All right, we're going to talk about running a simulation study and go through how we might code this up in a relatively compact, modular, and extensible way. So here we're imagining running a simulation study in R where we're comparing parametric and non-parametric estimators. Here we're imagining we have a single feature x that is drawn IID uniformly on the interval 0, 1, and we observe these xy pairs where y is some function of x plus IID mean 0 errors. And the errors here are going to be normal 0, 1. And we're going to think about in this simulation study considering different f's and also different estimators and trying to evaluate the appropriateness of each of those estimators for these different f's. And again, we're thinking about when are non-parametric regression estimators stronger than parametric regression estimators. So in each of these scenarios, for each of these methods, we're going to look at the mean squared error, where here we're going to average the difference between our predicted conditional mean f hat and f over our observed training points. So here we're going to think about estimating f hat using linear regression, polynomial regression on polynomials of degrees 2 to 5. And one can sometimes think of polynomial regression as a non-parametric method if you tune that degree and allow it to grow in sample size. Here we're not thinking about allowing it to grow in sample size. And finally, we're also going to look at a Nadaraya-Watson estimator with a box kernel, and we'll talk a little bit about choosing an appropriate bandwidth and how you might think about tuning that. But again, the goal here is to run this simulation study to do this evaluation. The two generative regression functions we're going to consider are a linear function f of x equals 2x, and this wiggly regression function f of x equals sine 2 pi x, which doesn't wiggle that much over the interval 0, 1, but does wiggle some. And again, we're really going to think about how we might structure our code to engage with this such that we could employ different types of estimators, more complicated estimators, and additional different regression functions without too much pain. And when we're thinking about this simulation setting, we are going to evaluate our estimators in each of these scenarios for a range of values of n and see how the performance of the estimator varies with n. All right, now before we actually do any coding, I find that it can be helpful to organize how we're going to write our code. So let's first just write the goal overall for the simulation that we're going to run. All right, so for each model or algorithm and each generative function, what do we want to do? We want to vary the values of n and then evaluate the expected error from each of these models or algorithms. I'm just going to put this on another line so I can see it all. So this again is sort of the overarching goal, and I find it useful to write this out. Let's actually make this a little bigger. And again, I'm not really writing code, I'm just going to write comments to myself. Could have written this in a notepad document alternatively, or handwritten it on a piece of paper or board. So let's break this down even further. Again, we're going to start by engaging with one model or algorithm, one single n value, and when we think about the expected error, we're going to imagine simulating a large number of times. So again, to simplify things as much as possible, let's think about what the code would look like if we only simulate one data set. So again, we're breaking things down to the sort of simplest possible piece we're going to have to run, and then we're going to build up from there. So again, I'll say breaking this down. Okay, so want to run one iteration of the simulation for a single n value, a single model slash algorithm, and a single f, conditional expectation or generative model. And when I do that, when I run this one iteration, what are my steps going to be? So step 1, I'm going to generate some data. Step 2, I'm going to train or fit my predictive model. And then for step 3, I'm going to evaluate that predictive model. And how am I going to do that? I'm going to need to look at the predictions from that model, look at the value of f at those same x observations, and evaluate the difference between those predictions and that true conditional mean. So again, I'm now considering the simplest possible thing that I need to run, and I'm breaking that down into steps. So now let's expand out steps 1, 2, and 3. So for step 1, generate the data, what is this going to look like? Well, step A is going to be generate the x's. Generate x's as, in this case, it's going to be uniform 0, 1. Step B is going to be generate the y's according to the x's and that f conditional mean function of interest. And then step 3, or step C, is going to be return a data frame with x's and y's. And again, I've sort of broken this piece down. We're going to write this in a function. And so one thing that I'm doing is I'm sort of breaking down my simulation study into the functions that I need and then into what I need in each of those functions. So now for step 2, train our predictive model. What is this going to look like? And again, maybe we could just start writing code now. I'm still going to be a little pedantic here. So maybe the first step is pass training data into predictive model fitting function. And for like a linear regression model, maybe this is the LM function. And then this is going to be pretty short. Step B is going to be return the output of the fitting function. So now finally, let's move on to this third step, this evaluate predictive model step. And so what are the pieces here? So the first piece is going to be we need to get predictions from our fitted model on a grid of x's. And in this case, I think in the problem I said the grid of x's should be the training points. The next thing we're going to need to do is we're going to need to evaluate that true conditional mean on that same grid of x's. So get values of true conditional mean, that f function, on the same grid. And then the last step is going to be calculate MSE, so the mean of the squared difference between those two sets of values. And then, once we do this, we're going to want to wrap this in something like a replicate function to, rather than just run one iteration, run a large number and average them. And then we're going to want to wrap that in like for loops so that we can consider multiple different values of n and maybe multiple different algorithms and multiple different conditional mean functions f. So wrap this in a replicate function plus loop over values of n and f's and algorithms. So from here, now we can actually start writing some code. All right, now let's try coding this up. So let's do this one function at a time. So we're going to start with this function to generate the data. So beginning here, let's create a function maybe called gendat. And what should it take in? Well, for now, we're just going to have it take in n, the number of observations that we want to generate. So again, we look at these steps. The first is to generate these uniform x's. So x is going to be uniform random variables from that range 0 to 1, and we want n of them. Now, for y, we're going to modify this in the future, but for now, we're just going to use that simple linear conditional mean, that first conditional mean we wanted to generate from. Again, we're going to allow this to be more flexible next. So we'll say y is 2 times x. Remember, that was that first conditional mean we wanted to engage with, plus random Gaussian error. There are going to be n of these, and I'm going to make a note to myself, note, change this to be more flexible. So we'll see we're going to change this, that 2 times x into an argument that we pass in eventually. And then that last step, step C, says return a data frame with the x's and the y's. So I'll create a data frame. Dat maybe is what I'll call it. And the x's, maybe I'll call x. The y's, maybe I'll call y. This is maybe not the greatest notation. Here it says create a data frame with 2 columns, a column x and a column y. And the value in x should be this that we had previously called x. And the value in y should be this that we previously called y, and then return this. Perfect. So this is our first function to generate the data. And again, we're going to modify this in the future to be a little more flexible. All right, our next function is going to train a model. And here, let's just train a linear regression model. Again, we're going to want to make this more flexible as well to, for example, allow us to train a polynomial model. But to start, it's just going to train a linear regression model. So we'll call this function maybe train mod. It's going to take in data, right, as we say in 2a, and we'll call that dat. And again, that's going to be the output of gendat. And here we're going to fit a linear regression model. So fit, we're going to create this object that runs linear regression. And it regresses y on x. And the data frame that it uses is going to be, again, what we pass in called dat. And dat is going to have 2 columns, an x and a y, which should match, again, the data frame we were creating here. And then we're just going to return this object. And we're going to be able to make predictions with this object. Perfect. And again, we might want to make this more flexible and allow ourselves, rather than just training a linear regression model, training a polynomial regression model and maybe writing another version of this to train a Nadaraya-Watson model. So the next thing we want to do is evaluate our predictive models. And here, it's going to take in that fitted model that we're going to return from the train mod function. And eventually it will take in the conditional mean function and evaluate both of these on the training points. So it's also going to need to take in dat. For now, we're going to hard code a couple of things and then again modify in the future to make it more flexible. So maybe I'll call this function evaluate model. And what am I going to pass in here? I will pass in fit. This is going to be, again, that fitted model from train mod. And maybe I will pass in xgrid, and these are going to be the x values where I want to do my evaluation. And for now, I'm going to hard code in that conditional mean function 2 times x. And again, this is going to be long-term poor coding. But in the short term, we just want to sort of build something up, get it to run, see that it works, and then generalize things and pull things out of our functions so that they can work more flexibly. And so that we can then eventually slowly build up our whole simulation study. All right, the first thing we want to do is we want to get our predictions along this grid of x values. So we say maybe our object we'll call preds, and we are going to apply the predict function, which can take in our fit from our linear model, which we're calling fit, which we pass into this function. And it takes in what we want for our new design matrix, new_x. And in this case, it wants it to be a data frame. So we say data.frame x equals x underscore grid. So what happens here? Well, we create a data frame with a column called x. And the values that we use for that column are these x grid values that we're going to pass into evaluate model. Perfect. So this is going to give us these predictions from whatever fit is. In this case, it's going to be a linear model we fit to the data. And it's going to get those predictions along this grid. And now the next piece is we actually need the values of the conditional mean along this grid. So cond mean vals. So that's going to be, for now, I'm going to use this, again, linear conditional mean function. Again, I'm hard coding this in just to get something working. And then I like to engage in this way. Then after I get something working and I can see how it works, I'm then going to make notes to myself. These are magic numbers and we need to pull them out. And I'm going to pull them out and have them passed into these functions. Again, we'll see as we go. For this particular generative function, the function f of x equals 2x, our first example that we wanted to run in our simulation study. Again, the value of the conditional mean along this grid is 2 times the x grid value. But again, I'm going to make a note. Change this to be more flexible. And finally, I'm going to calculate the MSE, which is going to be the mean of those predictions minus the true conditional mean values squared. And then I'm going to return that MSE. So I've now built out these 3 functions that will engage each of the individual parts of this simulation study, generating data, training the model, and then evaluating the model. I now am going to need to write one function that glues all of these together. And I'm going to call this maybe run1 eval. And this is going to take in an argument n, which says, okay, how many observations, data points do I want to generate? So, okay, I want to generate n data points. So the first thing I do is I create my data object using the gendat function. So this is going to create these xy pairs, n of them. The next piece is I want to use my train mod function to create a linear model based on that data. And the final piece is I want to calculate the MSE from this model. So again, I'm going to use evaluate model, and I'm going to pass in fit, which is the output of that train mod function, and then dat $x, those are the training x values where I want to evaluate the MSE. And the final thing I want to do is I want to return MSE. And just to note, a lot of the arguments and variable names that I use here happen to match the names of things returned from each of these functions. That's not necessary. That's just for me to do some bookkeeping. I think some would argue that this is actually not ideal coding practice, because you can end up accidentally accessing or engaging with global variables that are named the same thing in two different places. So anyhow, don't worry about that if it didn't totally make sense to you, but just note that sometimes I have matching of variable names that you don't necessarily need to have. All right, so we now have all of these functions. I'm going to execute them to get them into my workspace. And now finally, so if I run this run1 eval, we can look at what we get, maybe with 100 observations. What does this do? Well, it generates a set of data, 100 observations, 100 xy pairs, where y equals 2 times x plus Gaussian noise. It then fits a linear model to that, and then evaluates the predictions from that linear model versus that true conditional mean, f of x equals 2x, at the 100 observed training points. Gets an MSE for this. So if this is a simulation study, though, so I don't just want to do this once. I want to do this a bunch of times. And so what I'll do is I will wrap this in a replicate statement. So maybe I have n reps. How many times do I want to run this? Say 1,000. Okay. And then I'm going to use replicate, which runs a given command some large number of times and concatenates all the outputs. So replicate, the first argument is the number of times I want to run the command. The second argument is the command. So let's say, okay, run this experiment that you just ran once, only now run it 1,000 times. So I can do this, and I get 1,000 mean squared errors. And I sort of, again, want an expectation over those, or a Monte Carlo average over this. So what I do is I now wrap this and look at the mean of all of these. And this says mean squared error averaged over all of those simulated replicates is roughly 0.02. Great, I've done this for n equals 100, but when we run this simulation study, we are interested in seeing how the mean squared error varies as we change n. So let's write a little bit more code, and ideally we would wrap all of this in functions. So rather than a single n, let's make a vector of n's. I don't know, maybe we'll start at 30, then go up to 50, 100, 500, 1,000. You can choose your own range of n's if you would like. And now let's run a loop and loop through and each time generate these mean squared errors. But let's make a little container to hold all the mean squared errors that we are going to calculate. So I'm going to make a vector filled with zeros, and the length should be the length of n's, because we want one MSE calculation for each of these different number of observations we're going to simulate. So now we're going to wrap all of this in a for loop. So for I in 1 to length n's, what do we want to do? Well, the n that I want to use at each replicate is the ith entry in n's. And then let's populate MSEs, that ith entry, using, it's going to be exactly this command, except now, rather than 100 here, we have n. And here we go. So now Let's run these lines, and we can look at MSEs, and we see these are decreasing, right? For n equals 30, our MSE is like 0.07. For n equals 50, it's like 0.04. N equals 100, it's like 0.02, etc. And if we want, we could plot this. So plot n's versus MSEs, maybe type equals L. Right? And again, what we see is as the n that we're using increases, the MSE decreases. All right, now before moving on, there's one last thing I want to do. And that is, it was really bad form in evaluate model and in GenDat to hard code this f of x equals 2x. So I'm just going to pull that out really quickly. So how am I going to do that? I'm going to say cond mean linear. So this is going to be one of my conditional mean functions. It's going to take in an x, and it's going to return 2 times x. And I'm going to have one of these for each of the conditional means that I might want to engage with in my simulation study. And then GenDat is going to take in some function, some argument, which is going to be a function called conditional mean. And where before I had 2 times x, I'm now going to have cond mean of x. Similarly, if we go all the way down here to evaluate model, where I had 2 times x, I'm now going to have cond mean of x grid. And now I need to pass in this cond mean function. And finally, when I say run one eval, in addition to n, I'm going to need to know the conditional mean function that I'm using for generating my data. And so I pass in something that I'm going to call cond mean, and then my data, when I generate it, again, it needs this input cond mean, and that's because up here, that was one of the inputs that I required. And similarly here, when I evaluate my model, now again, I need cond mean in here. So just this last piece, we now cycle through this, we run all of these functions again, and now, again, if we run through all of this, we should get essentially the same result. Now there's one last piece to change, and you can see I didn't change this and I just got an error. And that is in this replicate command where we say run one eval n. Rather than just passing an n, remember, run one eval now has to take in both n and the conditional mean function we're using to generate our data. And again, for now, that's going to be cond mean lin, right? We're using the linear conditional mean function to generate our data. When we actually run the full simulation, we're going to cycle through and sometimes use that conditional mean function and sometimes use that other smooth conditional mean function. So again, we go back down here, and run one eval now needs cond mean lin as a second input. All right, so now we run through this all as a final step, and we should get mean squared errors that look very similar to what we got before. They won't be the exact same because we didn't set a seed. But again, when we plot them, we see they look extremely similar. So just as a final piece here before moving forward, what did we do? Well, we wrote these pieces of the engine that generate the data, that train the model, and that evaluate the model. And here we are allowing ourselves, as we run all of this, to specify as an input what the conditional mean function is. And one neat thing about R and just the way programming works in general is that this input is not a number, this input is a function that we then apply to our x's as we move forward. All right, now we want to modify our code to do basically the same thing we just did for the conditional mean, only now for our model training function. And again, what we did was we took the conditional mean, and rather than hard coding it in, we allowed that conditional mean function to be passed in as an argument to everything that we engaged with. And so again, let's try to do that with our model training function. Let's, instead of hard coding it in as fitting a linear model, let's allow ourselves to write a function that takes in data and fits a model and pass that through this whole engine. So let's scroll down and see where we engage with that. So again, recall the way this works is We first generate our data, we then train our model, and then we evaluate it. And we do all of that in run one eval. And so if we look at this run one eval function, what we see is in here, we call this train mod function that we had written up above that trains a linear model. However, this is sort of hard coded in. It's not actually its own input into run one eval. So what we're going to do now is we're going to allow ourselves to use different train mod functions, and we're going to have train mod just be an input to run one eval. And again, it's a function now, a function that we input as an argument into run one eval. And up here, maybe rather than calling this train mod, we'll call this train mod lin, because this trains a linear model. So again, we've modified our code a little bit. We've created a function that we now have to pass into run one eval. And so where do we finish modifying our code? Well, again, we scroll down here, and in this for loop that we have at the bottom that actually engages with all of the functions that we have written, in this replicate statement where we actually run our simulations for a single value of n, we call run one eval with n, the number of observations we want, cond mean lin, this conditional mean that's going to be a linear function. And now, what do we want? We want to say what model we're going to use for training. So train mod lin is going to be passed in. And so, again, what have we done? We have now allowed ourselves to pass in as an argument the function that we want to use to train our model. So if we go back up and run through all of this again, what do we see? Well, we don't need this statement anymore. Right, everything is running. And again, the code should execute and do basically what it did before. We've just sort of pulled out some of the pieces that were hard-coded in. So we see our MSEs look relatively unchanged, and our plot looks essentially unchanged up to a little bit of Monte Carlo error. All right, and now I'm going to pull out some of the comments that I made for myself, because I don't need those anymore. And I'm going to make two new notes. So the first note is that I want to write some more models, or training functions. Maybe I should call it model functions. And the other is I need to write some more conditional mean functions. And in fact, as we recall in the original prompt, there were two conditional mean functions. There was a linear conditional mean function, and then there was a sinusoidal conditional mean function. So let's write both of those. And the sinusoidal conditional mean function took in an x and returned the sine of 2 times pi times x. Right, and so these are two different conditional mean functions that I could pass into that engine, right, that gendat function. And then in terms of these training functions, we actually have a number of models to engage with. I'm going to write one additional model right now. We'll see there might be a cleverer way, rather than hard coding many of these in, to allow ourselves to fit, say, polynomial models of various degrees. So let's change train mod lin to train mod, say, quadratic. Say we want to fit a degree 2 polynomial model. So I'm going to create a new function called train mod quad. And now in here, rather than fitting a linear model of y on x, it's going to fit a linear model of y on a polynomial of degree 2 in x. And I could do this, make a separate function for degree 2 polynomial, degree 3, degree 4, up to degree 5 if I would like. We're going to stick with this for now. We'll save our code. We are going to get these, say, new functions into our workspace. And then, again, if we just want to play around with things, we could modify our code down here when we run our simulation, and we could change either the conditional mean that we're generating from or the model we're using for training. So yeah, let's try changing the conditional mean and see what happens. Right, I posit for a sinusoidal conditional mean, fitting a linear regression model should not do very well. So let's see what we get. And surely enough, we see that the mean squared error essentially almost doesn't decrease at all as we increase the sample size because there's this misspecification bias. And instead of a linear model, we could try a quadratic model and look at what the MSE would be in that case. In general, these more flexible models will allow us to have less misspecification bias, though for sinusoid it's a little bit funny. The parity of the function means that, in fact, going from a linear model to a quadratic model won't really improve things, but going from, say, quadratic to cubic will. Now, to build up those polynomial models, there are 3 approaches we could consider. One is we could just hard code in 5 models here, right? Linear, quadratic, cubic, etc. Another is that we could write a function that's just called train mod poly, say. Train mod poly that takes in 2 inputs, the data and the degree of the polynomial. And this would also work perfectly well. One thing that is a little complicated here is that now every time we call this function, it expects not just to have data, but also to have the degree of the polynomial passed in. And so again, this would be a totally fine way to go. However, if you did decide that you wanted to use this when we engage with other pieces of the code, for example, in run eval, when we run this train model function, we would also need in here to pass in the degree. And so run one eval would also have to have the degree passed in. So again, that would be one totally reasonable way to go. And this final function could subsume all of these. There's one other approach that I really like. It's called using a closure. And a closure in this case is basically a function that contains its own little data environment that you don't necessarily need to pass in. And you can also think of it in this case as we are going to write a function that creates and returns a function. So I'm going to use that approach just because I think it's a little bit cleaner. Maybe it's a little bit fancier as well, but I really like it, and I think it's a very useful programming pattern. So let's see how this is going to work. So I'm going to call this train mod poly generator. So this is going to be, it's like a function factory. It will generate functions for me. And it's going to take in just a degree input. And so we're going to pass in a degree, and from that degree, it's going to create functions that look like these up here. So it's now going to create a function that I'm going to call, say, train mod. This is going to be a function that is going to take in an input dat, and it is going to fit, copy this line because it's going to be useful. It is going to fit a polynomial model of degree. For good measure, I'm going to return train mod. So again, this is a function that creates a new function inside and returns that new function. So let's see an example of how this might work. So I'm going to use this closure, this function generator, to create this function, or an alternative version that will do the same thing. So I would say train mod lin alt, and that is going to take train mod poly generator 1. So let's run this for a moment. And now if I run this line, what happens? What happens is now I have a function train mod lin alt, and that function, what did it take in? It took in this, right? This, when I execute that function on, say, a data object, let's imagine I had a data object and I type train mod lin, alt dat, what would it do? It would take this data object, that would come in here, it would then fit a polynomial with this data object, regressing y on x. What would the degree be? The degree would be whatever degree I had originally used in creating this function. In this case, it would be 1. And then it would return that fit. So again, this will do the exact same thing that this did. Similarly, if I wanted to do this for a quadratic model, what would I do? I would say something like train mod quad alt, that could be the name, and do the same thing, only now put in a 2. So the beauty here is that when we create these functions, while we have to specify the degree 1 or 2 or 3, etc., when we actually execute these functions, we don't have to specify the degree. That degree is stored in that environment that the function maintains. So we can now do something clever. We can make a list of functions of degrees 1 up to 5. And then we can just engage with that list and pass those functions into our simulation engine. Before moving on to that, though, it might be very useful for you to pause for a second and just try to understand what this code was doing and how this code worked. All right, so I'm going to remove these for a second. And remove these because we won't need them anymore. And I'm going to say train mods is going to be a list for I in 1 to 5. I want to cycle through degrees of polynomials up to 5. Train mods I, the ith element of this list, I want to generate a model trainer of degree I. Before we try things out, there's actually one more little subtle piece that we're going to need that's due to a peculiarity in R. And that is, in this function, we actually need to add the line force degree. And this is due to something called lazy instantiation in R that I'm not going to go into detail on. But in particular, when we want to create these model trainers and put them in a list, if we don't do this, we get actually slightly funny behavior. So let's go back. Let's run this. Let's run this piece again to create all of these polynomial model trainers. And now, if we go all the way down here, what we see is we can modify the code that we have here from what we had hard-coded to train mods and then elements of this list. And again, each element of this list is itself a function that can take in a data object and will spit out a trained model. So again, if we run these lines, what we should see is exactly what we got when we trained our linear model. So again, the mean squared error shouldn't really decrease here. Perfect, it doesn't. And if we go up to, say, our 5th degree polynomial, we've trained up to degree 5, we can just put in the 5th element of that list, which we generated using that for loop with that closure. And we run through this, and what we should see now is the mean squared error decreases in n. So let's see what we get. And perfect. Exactly. We see the mean squared error decreasing in n. And we can look at a plot of this. So now, as an additional step, we could try wrapping all of this up together. So what do I mean by that? Well, let's try to put all of this in sort of a big set of for loops. So now, rather than having 2 different conditional means with different names, maybe we can create a list called conditional means. So cond means, maybe that's a list, and maybe cond means 1, we can make this linear conditional mean, and cond means 2, we can make this sinusoidal conditional mean. So again, once we run these lines, we'll have this list of 2 conditional means that we could fill out further if we wanted to. And again, my code is not organized particularly well. At the end of this, I might go and try to organize my code better. Again, we have now this list of functions that we have generated. Perfect. And now at the very end, we get down to this simulation code. And what did we do? Well, here we ran this for a single conditional mean and a single training model. And so what we might do instead is we might make a list of mean squared errors and then maybe a 2-dimensional list, and then we could cycle through our conditional means and cycle through our training models, and each time generate data according to the conditional mean, fit according to those various training models, and build out plots like this for each of these different models and each of those different means. So ideally here, to do this, we would wrap this in a function, right? So we would take what we had before. We could say run one sim group, and this is going to be a function that will presumably take in a set of n's. Maybe we could call it n vector if we wanted to. It would take in a conditional mean function, and it would take in a training model function. Right, and what would it do? Well, it would just do exactly what we were doing before, right? It would run through, it would calculate all of this, it would output our mean squared errors. Excellent. And then we just probably want it to return these MSEs. So now we can create this function, and we can see that if we run this function and we pass as input, say, those n's that we generated up here, and we pass as input, say, for the conditional mean, oops, we have to make sure we fix that. We need to make sure that the functions we use match the arguments that we input. So what might we want to use here? Maybe we use cond means 1, right? That was our linear conditional mean. And maybe we use train mods 1, and that's our linear polynomial fit. Right, and so now, if we, again, just re-execute that and run this line, what happens, it runs through that whole set of simulations, again, generating from a linear mean and fitting with a linear model. Right, and we could also generate now, say, from a sinusoidal mean and fit with a linear model. And this is just based on how we define that cond means list. Perfect. So again, these are the outputs that we've been seeing this whole time. It's just now the code has been chunked out into functions. And again, sometimes you can a priori know exactly how to chunk out the code into functions. This programming exercise has been a little bit messy as I've been writing pieces and then chunking as I go. All right, now as a final piece, perhaps, we want to cycle through using a for loop and run this run one sim group for each of the different conditional means in each of the different training models. So to start, I think I'm going to make a data frame that I'm going to use to store all of these outputs, these MSE outputs. So it's going to have a column called MSE that I'm going to make numeric. It's going to have, I think, a column called conditional mean that I think is just going to be the index that I'm also going to make numeric. And I'm just defining the columns now. I'm setting them equal to numeric variables with no entries. And then I'm going to have the training model ind, which in this case, again, is going to be numeric with, for now, no entries. And I'll call this output. And now I want to cycle through all of my conditional mean generators and all of my training models. So maybe for I in 1 to length cond mean. And then for j in 1 to length, length train mods. And now I can basically run this, right? Cond means I, train mods j, and maybe I'll call this MSEs, gets that. So now I want to take this MSEs and I want to turn it into a 3-column matrix where the second column is the index for the conditional means and the third column is the index for the training mods. So I'll call it new output that I'm going to append. So maybe I'll say new output is data.frame, MSE equals MSEs, cond mean equals I, train mod equals j, because I and j are those indices. And now I can concatenate this to my output. So output is rbind output new output. And again, this should continue to stack these on top of each other. So let's see what we get. All right, and now we can look at output. And what do we see? We see a bunch of different values, right? These simulation values are now stacked on top of each other. And now looking at our output for a moment, I realize in fact that I'd really like to have another column that has those n values that were used for generating these simulations. So in fact, I'm going to go up here and I'm going to create a new column in output, n, which is going to be numeric. And I am going to, and when I create my new output, I'm going to add this column n, and it's going to be equal to n's, which again is something that I've been engaging with earlier. And so now I can rerun this, and when I do, I'm now going to have a new column with those values of n used in each simulation. All right, now we can peek back at output, and what do we see? We see we have that new column that has all of the values of n for each of those simulations that we ran. All right, now as a final step, let's plot our output. We're going to do this using ggplot as it's a little bit cleaner and quicker. So the first thing we want to do is load in our library ggplot2. Great. And now, again, we can actually do this pretty slickly. So we call ggplot and we pass in that output data set. And we have to define our aesthetics. X is going to be n. Y, in this case, is going to be the MSE. And we want to break these up so that, say, each of the different training model procedures gets a different color. So we would say color equals, and rather than saying train mod, that's numeric and going to give us a little bit of trouble. We're going to make sure that that's indicated to be a factor, as.factor train mod. Perfect. And now we have to say, hey, we actually want this to be a line plot. So we say plus geom line. And then we want probably a different plot for each of our conditional means. So we use the faceting commands, facet wrap, and then tilde cond mean. Excellent. And let's make this plotting area a little bit bigger and run this. And what do we see? Excellent. So on the left, we have our first conditional mean, that linear mean, and we see what the mean squared error looks like as a function of n for each of our 5 models. And we see, in fact, the linear model does best. All of them decreases and gets large. The quadratic model does second best, then the cubic, the 4th degree, then the 5th degree. This makes sense as there's no model misspecification in any of these, right? And the higher order polynomials have a little bit more variance because they're fitting more terms. And then we can look at trying to fit this sinusoidal model. And what do we find? We find that the first and second order models do incredibly poorly on the right, and that, you know, the third and fourth do better. The fifth, in fact, will even do a little bit better. And this is, there's some parity here that's based on the parity of the sinusoid. So anyhow, again, we could now expand this, use different conditional mean functions, use different model fitting functions, higher order polynomials. Ideally, we'd expand this to use Nadaraya-Watson, but this video has gotten a little long, so we may have to push that to another video. Now, as a last piece here, I want to look at a cleaned up version of our code, because again, the old code ended up being a little bit of a mess, so I just spent like 3 minutes and refactored it. And now, again, the sequence of the code, I think, makes more sense in terms of the organization once we've written all the code, although it would have been hard maybe from the get-go to write the code in this way. So we start by loading in libraries we're going to use. In this case, we're going to use ggplot2 at the end to plot things. The next thing we're going to do is write a bunch of functions that we're going to use in our simulations. Now remember, we're going to use 2 different conditional mean functions and 5 different predictive modeling functions. So we define those 2 conditional mean functions here, our linear and sinusoidal conditional mean functions, and then we stuff them in a list so that we can iterate through later. And again, we could add more here if we wanted. We then move on to our predictive model training functions. And remember here, we use this sort of cute closure to allow us to develop polynomial fitting functions up to whatever degree we were interested in. Here we choose up to degree 5. And as one quick reminder, this force command is a little funny, but has to deal with lazy instantiation in R. You'll find that the code doesn't quite work if you don't have that. So anyhow, what we do at the end of this is we create this list called train mods that has the 5 models we're going to use, 5 polynomial models to fit our data. And just as a reminder, train mods is a list. Each of the elements of that list is in fact a function. And similarly, cond means is a list. Each of the elements of that list is a function. So awesome. So these are going to be things that we then pass in, and you could add more train mods if you want. In future, maybe we'll add a Nadaraya-Watson estimator, which will require a little bit of slickness and more use of closures. So, okay, now moving on, we're going to have our simulation engine code. This is going to be a collection of functions that we're going to pass those conditional means and training models into that are then going to run our simulations for us. So we have sort of our overarching function that takes in a vector of n's that we want to run our simulation study under, and takes in one conditional mean function and one training model function, and then runs a set of simulations to evaluate the mean squared error for this training model under that conditional mean with this vector of n's. So again, it's a short function. As a workhorse, it uses this run one eval that basically does what we were doing up here, only now for a single n rather than for that whole vector. So the top function loops through and calls this bottom function for each n. And now this bottom function, what does it do? Well, it has to generate data, fit a model to that data, and then evaluate that model. And so it uses these 2 subfunctions, genDat to generate data, and evaluate model to evaluate our model. And again, it takes in the conditional mean function and the training model function that we specified and passed in. So these are all of the functions that we ended up writing before. So now what we do is we just call that outermost function, right, that run one sim group. Only we have to pass in some other parameters. We need to loop through and call this with all of our conditional means and all of our training models. And so that's exactly what we do. Here we set a seed for good form, and then we say the number of repetitions we want for each of those MSE points. Here I'm using 1,000. You could use more, or if it were too slow, you could try using less. We have our vector of n's. Here I use 30 up to 1,000. Again, you could imagine using more n's or larger n's, etc. I create that output data frame that's going to house all of my outputs. Then I cycle through. I have these 2 for loops looping through both conditional means and training models. And each time I run this workhorse function, run one sim group, that calculates all of those MSEs. I then pass that in and stack that on top of the output that I already have. And so at the end of this for loop, I have that big data frame that has all of my outputs stacked. I could then peek at that output, and finally at the very end, I can use ggplot with all of this to calculate all of those curves. So again, this is the clean version, and once you have written a fair number of simulation studies, then sometimes you can just straight up go into this. You don't have to write it the other way and move the functions out. But I think the other way is informative for helping us think about how we write this when we're not really sure what each of the steps are going to be.